So in this video, I'm going to explain Thevenin and Norton equivalent circuits. So Thevenin and Norton equivalent circuits are are circuits that basically are equal to more advanced circuits. So there's a lot of stuff going on, and you want to know what the output is going to be, how it behaves in general, the output of it, right? And it helps you do that basically. You know what I'm saying? No matter what, let's say you wanna know how it's gonna react when you put in a load. You can do that without having to reanalyze a huge circuit. So yeah, we're gonna and a Thevenin circuit looks like this, where it's VTH and RTH, and the S missed, and this is where the load will go, and Norton equivalent circuit looks like this. And this is where the load will go here. This is the circuit. And note that these are equal, and you can relate VTH to IN using Ohm's law, basically, VTH or IN, whatever. So yeah, you can do that. So let's just do an example. Okay, so for the example, we have a circuit with an 8-volt voltage source and 3k ohm resistor and 5k ohm resistor, and we want to turn it into a Thevenin equivalent circuit and an Norton equivalent circuit. So what we're going to do is we're going to find the VOC, because that is equal to the Thevenin voltage. So we're going to find, using VDR, the Thevenin the VOC basically. VDR is voltage divider rule. So because we're looking for the voltage across this resistor, right? We're going to use voltage divider rule, and we get 5 volts. So we know that this is 5 volts. Now we need to get the RTH, which, remember, would be the same as this, and we can use that to get IN. To get IN, we could also just short circuit this, and if we short circuit this, we can then use the ratio of RTH equals VOC over ISC. Once we get that IC would become IN, VOC would become VTH. But we're just going to go and do the off. We're going to turn this off instead, so I can show you the other resistor calculating way, which is going to be, once we turn it off, we get a circuit that looks like this, where it's going to be 5k, 3k, and this is A, this is B. And as you can see, they're in parallel, so R equals 1 over 3k over 5k, which is 15k over 8 ohms. So that equals our RTH, which is also equal to RN. And using that, we can actually get the IN. So we could say, we know that VOC divided by RTH, VTH, equals IN. So that's just this is 5 over 15k over 8. That's 40 over 15k. So 8 over 3 milliamps. Now we're just going to like this. That would be like this. 8 over 3 milliamps and 15k over 8 ohms. This is not fun circuit. However, and yeah, this is how that works. But the problem is, you can only turn off independent sources. You can't turn off dependent sources. So for that you need to use the test signal method. So let me get that set up. So this is the example that has a dependent source. As you can see, it's a 2 times gain here. So whatever voltage it across this, it pumps out like the current twice as large this way. So we can use KC. We can basically now just have to solve for the VTH to get the to start off. Right? We can get the VTH using the same system. So let's use KCL here at VAB, and we get Vx over 1K, because the current going through this way, is equal to VAB over 1K, current going through this way, and the current going through this way. We can also use, we can say that the voltage across this is 5V minus VAB, so Vx equals 5V minus VAB, and we can like plug those in and solve. So let me solve that. Okay, so I solved to solve the system of equations, and I got that VAB, which is VTH, is 5.0025 volts. I can also confirm that on Volstad. 5.003 volts right here. So that's good. Now we can run the test signal method to check for the RTH. So what we do is we turn off the source here, and we instead run a test signal through across the terminal like this. So what I'm going to do is I'm going to run a 1 volt test signal across, and I'm going to look for the current going across it. But you could also run a current source and check for the voltage across it. I'm going to go and run the plus voltage source this way. So let me set up the circuit and I'll show you. So basically it looks like this, and we can use KCL to solve for ITest. Basically we know what IV is, and we'll get ITest, and we can just basically say that the RTH is equal to the V test, which is 1 volt, divided by the I test, which is what we're solving for. So yeah, let's use KCL to come up with the KCL equation. So since I test is going into this node here, right, we have I test on this side, and we have kind of going this way. And also note that the Vx is opposite, so Vx here is -1, so we can use that into the equation. But basically we get 1 volt across this resistor, so that's 1 volt. The current going this way, and going this way. So we get 1 volt across this resistor, 1K. 1 volt across this resistor, 1K, and then 2 Vx going this way. Vx is -1, so that becomes 1 milliamp plus 1 milliamp minus 2 amps. So we get negative 1.998 amps, because I test. So RTH equals negative amps over 1 volt, which is nearly oh my bad, opposite. Negative 1 volt over 1.998, which is nearly 1/2, but like a little bit less. And I think according to my calculator, that was negative 0.5005 ohms. And as you can see, the resistance is like negative, which is because this guy can like actually change stuff. This can make it so that like it's almost like negative resistance, or really small, even though these are pretty large resistors. This changes it, and it makes it like negative, and that's how this circuit would be acting. That's why this helps. That's why we couldn't turn this off, because it would be doing like funny stuff here that we would just not notice. You know what I'm saying? So we gotta have this. That's it. Really helps you see, like, it makes it like, it affects things basically. So yeah, then that would make our equivalent circuit look like this basically. Yeah, we can also solve for the Norton equivalent just by using that thing I said earlier. So we got the same negative 0.5005 this right here, and then we would just multiply it. So we would divide basically, and we would I think it would be almost like wait, let me calculate it. IN equals to 98. So that's just gonna be like it is like basically like negative 9.995. Yep. Yeah. So, and I think they'd end up getting the same voltage across. So that's how Thevenin and Norton equivalent circuits work. And basically, just remember that you want to turn off all the independent sources, but you can't turn off dependent sources when you're looking for the RTH. And VTH is just the open circuit voltage, and Norton is the short circuit current, basically, when you're doing the equivalent stuff. Yeah. Thank you.